Being able to solve general triangles is very useful when it comes to solving word problems, because now we're no longer limited to situations where there has to be a 90-degree angle somewhere. However, these problems, in particular, problems involving situations where something is turning a certain direction and traveling and making movements, very easy for students to make mistakes here. And the reason why is because the intuitive thing that students do, which is just sort of throw numbers into the diagram, turns out to not work in a lot of these problems. And again, especially the navigation problems. So here's an example. A boat leaves port, travels for 10 miles, turns 20 degrees, and travels another 8 miles. How far is the boat from the port? And so conceptually, it's not too difficult here. You got a boat somewhere, and it is going to travel for 10 miles in some direction. Then it's going to turn by 20 degrees, and then travel another 8 miles. And the question is, how far is it from here to there? Right, so conceptually, there's nothing too complicated going on here. However, what students will tend to do is they will throw in this angle right here is 20 degrees. Now, if you think about it, what's really happening? Well, this is the direction the boat was headed. So the boat's traveling this way, and it turns 20 degrees. The part that's 20 degrees is not this part in here, but rather that part right there. And this is the thing that throws students off when they actually try to work through this problem, is that they just throw in the 20 degree at that vertex, but they don't really think about where it fits. And as long as you slow yourself down, and again, especially with these navigation type problems where you have something moving and then turning, if you do that, you will be more likely to get things right. And by the way, there's nothing in this problem other than some base intuition about distances that you might have that will tell you that you've made a mistake if you've labeled the diagram wrong. So it's really important that you get this part right. So if that angle there is 120 degrees, then that angle on that side is going to be 160 degrees, right? Because it's 180 degrees total. And now we have a situation where we have everything set up and we can now solve it. So let's take a look. Let's label that side C, and this side A, and this side B. We can see that we have side, angle, side, where the angle is a 160 degree angle. And that tells us we want to use the law of cosines to get the opposite side. So C squared is equal to A squared plus B squared minus 2AB cosine of gamma. That gamma is 160 degrees. A is in this case 10, so 10 squared plus B, which is 8 squared, minus 2 times 10 times 8 times cosine of 160 degrees. Now, there's nothing much we can do here except plug it in, so we can do this part by hand, but when we get to the cosine 160 degrees, that's going to be a calculator calculation. And so let's just do the whole thing in the calculator. This will get us the value of 314.3508. So to get C, we take the square root of that. C is equal to the square root of this thing, which is about 17.73. And this tells us that the boat is approximately 17.73 miles from the port. So this was the port, and that's the boat. And C is about 17.73. Now, what I said earlier about the intuition kicking in, if this angle were 20 degrees, and you were to write this out and do the whole calculation, you would find that this distance here ends up being relatively small. And if you think about it geometrically, you would realize that if you travel for 10 miles, turn a little bit, and travel for 18 miles, you'd expect your distance to be closer to 18 miles rather than closer to 0 miles. And if you did this calculation, you would find, again, with the wrong angle here, you would find that unless you had some geometric intuition that told you, wait, this number is too small, you could just do the calculation and not even realize it. And so this is one of those situations where it can be helpful to just take a moment and think about it intuitively. Does the answer really make sense when you sort of imagine actually doing this trip? And that will help you also to catch these sorts of mistakes. Here's another example. Two cell phone towers are 6,000 feet apart along a straight highway running east to west. A cell phone is north of the highway and based on signal delay is determined to be 5,050 feet from the western tower and 2,420 feet from the eastern tower. How far from the freeway is the cell phone? Now this problem has a lot of words again, and so we need to take a moment and just sort of think through all the bits and pieces. Two cell phone towers are 6,000 feet apart, so 6,000 feet apart, and I wrote it this way because we're on an east-west highway, separated by an east-west highway. So here's cell tower, let's call it A, and cell tower B. There's a cell phone somewhere to the north, somewhere up here, and it is determined to be 50-50 feet from one tower, and then 20 feet from the other. We are asked to find out how far this cell phone is from the freeway. We use C for cell phone. How far is it from the freeway? Well, when we talk about distance between a point and a line, we talk about the perpendicular distance. So we are interested in that distance, which we'll just call x. One of the hardest parts of this problem is actually this setup, getting this diagram here and getting all the pieces correct. So once we have this, we now have to figure out, well, how are we going to get x? Well, we can see some triangle stuff going on in here, except we don't know the length of this side. And so we have to sort of make some decisions about how we might try to proceed. In this case, let's say that we're going to take this angle here, alpha. If we could figure out alpha from the big triangle, then we can use the right triangle with the value of alpha to get the value of x. And so that's what we're going to work on. So let's first of all look at this alpha. Well, this alpha we can obtain by using the law of cosines. So if we have these two sides, and then this angle, and then that's a known side. So we'll have, let's see, how I'm going to label this. So A, so here's my A, that's my B, and that's my C. All right, so the angle that we're interested in, alpha, is between B and C. So A squared is equal to B squared plus C squared minus 2BC cosine of alpha. This alpha value is the value we don't know, so everything else is just a matter of plugging it in. Now you might find that there are versions of the law of cosines that actually have it already solved out for the cosine part. If you want to use that one, that's fine, but it's really just algebra getting from here to there. The numbers are going to get a little bit big, so I'm going to just not square everything out. I'm just going to write it in its form, and then when we get to the last step, that's when it's going to get dumped into a calculator. So A is going to be 2420 squared is equal to B squared. B is over here, 50-50 squared, plus C squared, which is 6,000 squared, minus 2 times 50-50 times 6,000 cosine of alpha. And you can see here, like if I were to write these out, they're going to be numbers in the millions all going on here. So let's go ahead and rearrange this. I'm trying to solve for cosine of alpha. So what do we have to do here? Well, one thing we could do is we can add this to both sides and subtract that from both sides, and that way our cosine term will have a positive coefficient, and then we'll divide by that whole denominator. So what do we say? So we're going to add this and subtract that. So let's think about that first. So the 50-50 squared stays. The 6,000 squared stays. We're going to subtract off the 2420. Whoops. 2420 squared. And then since we moved this to the left side, this part right here becomes our denominator because we have to divide by whatever the quantity that is. 2 times 50-50 times 6,000. Right, so we're going to take this value, we're going to plug it into a calculator, get cosine of alpha. This value turns out to be 0.9183. You can use a calculator to get the value of alpha here. Now we do need to at least think about this, but it'll become clear why this doesn't matter so much in this particular situation. But cosine of alpha, alpha is going to be some angle. It's equal to a positive value. Cosine corresponds to the positive x direction. And so we're going to get an angle in quadrant 1 and an angle in quadrant 4. The quadrant 4 value in this case isn't going to be very meaningful, right? Because this is supposed to be inside a triangle. If you have an angle in quadrant 4, it's either going to be a negative angle or it's going to be an angle bigger than 270 degrees. Either way, this makes no sense in the context of this problem. And so we can use that information to just say, okay, we really just want the top angle, which is going to be the 23.33 degrees. All right, so that's your value of alpha. Our goal is this value of x in here. And so I'm going to squeeze it in over on the other side. So we have a right triangle. We have our angle alpha, our unknown value here, and we know the hypotenuse is going to be 50-50. Right, so right triangle trigonometry. This goes back to our opposite adjacent hypotenuse stuff. In this case, we have opposite and hypotenuse, and that's SOHCAHTOA, so sine is opposite over hypotenuse. So sine of alpha, in this case 23.33, is equal to opposite over hypotenuse. So x is 50/50 times sine of 23.33 degrees. And then this is a value you can throw into a calculator, and you're going to get x is equal to about 2,000 feet, so 1999.8 feet. And that is the distance that this cell phone is north of the freeway.